All right, so this last quick video is just going to be how to do these calculations to find atomic mass and how to do a weighted average. Um, like I said, a weighted average is kind of like what your grade in this class would normally be. It weights different categories, different amounts. The weighted average for atomic mass is based on um, how common it is in its nature, its prevalence. So, for example, in this first problem right here, it says Cu, or copper, 63 of a 69.2%. That means that if you take any copper atom in the universe, there is a 69.2% chance that it's copper 63, and then there's a 30.8% chance that it's copper 65. And they're all mixed together. Like, very rarely, or naturally, it's never going to happen to where a sample is all copper 65 and none of it's copper 63 or something like that. You kind of have to force something like that to happen. Um, so a weighted average is going to take into account the masses and also the percentages while we work this out. So I'm just going to do this first example for you, okay, so that you can kind of see how it works. And then I'm going to let you try the second one on your own before I go over it. So copper 63, that means that I'm going to have a mass of 63, and then I'm going to multiply it by its percentage, or its weight. But I'm not going to multiply it just by 69.2, right? Because that would make it a very large number, and all of a sudden the average mass is going to be way larger than 63 or 65. So instead, you're going to multiply it by the percentage represented as a decimal. So there's different ways you can do that. You can just take 69.2, put it in your calculator, and divide it by 100 to get 0.692. Or you could just move the decimal place to the left 2 places, because that's what dividing by 100 does, essentially. So I'm going to multiply by 0.692. And then I'm going to add that to my 65 multiplied by its weight, which would be 0.308. Okay, put it in my calculator, add it all together, and it ends up as 63.616 or something like that. Now, this obviously is not the best sig figs ever, right? So let's talk about sig figs, everybody's favorite. I know you're so excited. So if I'm looking at 63 and 65, are those sig fig numbers or exact numbers? Are they measurements or are they exact? And the answer is that they're exact. If it's 63, it's 63. Protons plus neutrons is 63. There's no rounding involved or anything like that. So the 63 and the 65 are exact. They have no bearing on where I round for my sig figs. But the 69.2, that's probably a rounded figure, right? That's some sort of measurement that's already rounded. So my answer over here should be rounded accordingly. So 69.2 has 3 sig figs, 30.8 has 3 sig figs. So when I add those things together, it should also probably have 3 sig figs after I go through and multiply and whatever. So this should probably be 63.6. And then what's my unit? What are the units for atomic mass? The answer is atomic mass units, right? AMU. So you would literally write 63.6 AMU. Okay? So for this example down here, it's a little bit different because it's giving you an element, but it's not telling you what element it is. It's just calling it element X. It says it has 4 isotopes, 54, 56, 57, and 58. Okay? So before you even calculate, before you write any numbers down or anything like that, what do you think is going to be a good guess for the atomic mass? Take a second and think about it. So based on this information that we have, I would say that a good guess for the atomic mass would probably be close to 56. Pretty close to it, because it has the highest abundance. Okay? And by abundance, we just mean that it happens 91.72% of the time, right? It's got a big weight attached to it. So the other stuff, especially because one of them is smaller and the other two are bigger, are not going to pull it too far from that 56. Okay, so we know that our final answer should be somewhere close to 56. Otherwise, we did something wrong. Okay, so keep that in mind. Go ahead and pause the video right now. Try to calculate the atomic mass, and then after you're done, I want you to see if you can identify the element based on your calculation. So pause the video. All right, so the biggest mistake that people make when we go over this problem is usually they didn't move their decimals correctly when converting the percentages to decimals. You've got some extra zero placeholders that you've got going on here. 5.9% is not 0.59, that's 59%. And you should have been able to catch yourself if you did that, because you should have gotten a number that was huge, okay? So then 56 times 0.9172 plus 57 times 0.021 plus 58 times 0.0028. Okay, so it's got that extra zero on there because it's 0.28%. Now, as a quick note about sig figs, I'll do this in yellow. You are supposed to carry sig figs all the way through. Okay, so if you're looking at 54 times 0.059, 0.059 has how many sig figs? It only has 2. That means my answer from that should only have 2 sig figs, which is 3.2. And I'm going to add that to 56 times 0.9172. 0.9172 has 4 sig figs, so this would be 4 sig figs, 51.36. 57 times 0.021 would have 2 sig figs, which is 1.2. And then 58 times 0.0028 would have 2 sig figs, or 0.16. So now that I've gone through and I've done my sig fig rules for the multiplying and dividing, I can do my sig fig rules for adding all of this together. So now I look at my decimal places. This one goes to the tenths, this one goes to the hundredths, the tenths, and then the hundredths. So my answer is going to be rounded to the tenths place. So when I put all of this together, it ends up being 55.9086. But when I round it to sig figs, I'm only going to go to the tenths place, which is 55.9. And units are AMU. So I've done all that work. I figured out my atomic mass for this element. So now I need to identify what it is. So you should have looked at your periodic table, and you're looking for something that also has an atomic mass of 55.9. And the closest element for that would have been iron, which is Fe. And there you go. You use this information to calculate the average atomic mass. You used it to identify an unknown, which is a very common like lab exercise in chemistry, a very common problem. And you're a chemist already.